Okay, hello, and a warm welcome from the Canadian Institute for Cybersecurity. My name is Brian, and we have three of our top people presenting to you today, Somayeh, Vikas, and Mohammed. First, I'd like to give you a brief introduction to the Institute, which is located in Fredericton. And I know some of you may not be familiar with Canadian geography. So where on earth is Fredericton? So it's the provincial capital of New Brunswick. We're in what's called Atlantic Canada, comprising New Brunswick, Nova Scotia, Prince Edward Island, Newfoundland, and Labrador. We border the state of Maine in the US. And I think we have a particularly nice provincial flag. It's my favorite of all the provincial flags. Just a few fun facts. New Brunswick is about 80% forested, so we have quite a big lumber industry. We're also a major source of potatoes and blueberries, and you may all be familiar with the name McCain, who are headquartered here. And we have a slightly strange temperature record that's symmetrical. So the lowest was about -39 Celsius, and the highest is +39. Those occurred in the first half of last century, so it doesn't usually get that hot or cold. And the southern coast of New Brunswick borders the Bay of Fundy, and that actually has the highest tidal range on Earth of 16 meters. And another fun fact is a few years ago, there was actually a moose on the University of New Brunswick campus roaming around. That does not happen very often. UNB Security estimated that it was in its first or second year. I assume they meant its age. This is a photo I took just a couple of days ago of the campus. It's quite a beautiful place. It's on a hillside, and it overlooks the St. John River. University of New Brunswick's the oldest English university in Canada. And if this looks at all familiar to you, it may be because the university was featured in the Ed Sheeran and Taylor Swift video of Joker and the Queen last year. And who would have thought that? All right, so the Institute was the vision of Dr. Ali Gorbani, who was formerly Dean of the Faculty of Computer Science and is now Director and Canadian Chair in Cybersecurity. It was established to focus on transferring technology to industry to help fight cybercrime. This photo was taken a while back, but there are now over 100 people. And our strategic priorities are industry and government partnerships, education, fundamental research, and knowledge sharing. And if any of you have any questions about us, please don't hesitate to email. So regardless of where you are in the world, you can rest assured that we will welcome you. Our master's degree cohort has over 80% international students from over a dozen countries. Master's students who are sponsored can also extend their training with a 4-month internship program. And if you're interested, you can also become an academic member of the CIC for free. We also take a long-term view here, and well, actually the day before yesterday, we hosted a Cyber Titans national competition of high school students. And this is part of community outreach to develop cybersecurity interest through schools. So this shows you some of the graduate destinations we have. Our graduates are sought after across the country and beyond. And some go on to work in UNB itself and government. So there are several ways that organizations can partner with us, such as chairs, consortiums, grants, student sponsorships. And we also offer a multi-year membership scheme for companies. We have 14 memberships and partners today, including IBM, MasterCard, National Research Council Canada, Rogers, McCain, as I mentioned earlier, GNB, and Siemens, to name a few. And recently, we acquired a membership with a private university in Togo, West Africa, called IPNET, to train their teachers in cybersecurity. Also be aware that we offer free data sets on our website. These are very popular. The latest was released the day before yesterday, IoT 2023. And yesterday also the new Truth Seeker data set is available. So please visit our website for access to those. All right, so now we're coming on to the presentations. We have, as I mentioned, 3 excellent presenters for you. I'll hand over to my co-host, Pam, to introduce you to our first speaker in a second. Please ask them lots of questions. They love questions. And thank you for joining us. Pam.
Thank you, Brian. So welcome again, and welcome to the Canadian Institute of Cybersecurity. My name is Pamela Kitchen, and I have 2 roles here at CIC, operational managers as well as project manager. And I have the pleasure of introducing my colleagues today who will be speaking with you on various subjects related to post-quantum. We will start off with Mohammed, and Mohammed will be speaking to Beyond the Hype, identifying the true quantum secure algorithms in the quantum era. Mohammed Al-Darwbi earned his Bachelor of Science degree in Computer Science from Darmar University, Yemen, and his Master's in Science in Computer Networks from King Fayed University of Petroleum and Minerals, Saudi Arabia. Currently, he is pursuing a PhD here with us at the Canadian Institute of Cybersecurity, or CIC for short, at the University of New Brunswick. And as Brian spoke, the University of Brunswick is within the capital city of New Brunswick, which is Fredericton, Canada. Mohammed is researching quantum safe and quantum key distribution for his thesis. His research interests span quantum computing, post-quantum cryptography, quantum key distribution, key management, intrusion detection, smart grid security, digital forensics, and cyber threat intelligence, as well as many other areas within the cybersecurity realm. So I'd like to welcome Mohammed, if you could start us off.
Thank you, Pam, for the introduction. Let me share my screen. Welcome, everybody. Today, in our session entitled Beyond Classical Cryptography, Feasibility and Benefits of Post-Quantum and Hybrid Solutions. I'll be talking and 2 of my colleagues, Somayeh and Vikas. So, and I will start my presentation first. So my talk will be focused on identifying the true quantum secure algorithms in the quantum era. In my talk, I'll give a brief introduction to quantum computing, and then I'll move to the key milestones that helped in achieving the quantum supremacy. Then I'll move to the quantum threat that brought us here today, which is the quantum computing might target our secure systems. Then I'll go over the types of quantum computers that they actually pose threat to security. Then after we explore the threat, what are the solutions? And then we will identify which of those solutions that they are really secure for the future. Let's start by introducing qubit. So qubit, which is the quantum bit in the classic world, So in the classic world, we have classical bit. The bit, it's the smallest storage unit in the computing, which can store either 0 or 1. However, in the quantum computing, we have what's called qubit, quantum bit. And the quantum bit, the qubit can store 0 and can store 1. But the great thing about this thing is it can be in the superposition, which helps in storing both 0 and 1 at the same time. It's not only 0 or 1, but it's both at the same time, and we can do so many things on it as if it is both states at the same time. One of the great phenomenon in quantum mechanics is called quantum entanglement. Entanglement, it's a probability that allow two or more qubits to be linked to each other, which means their measurements correlate, meaning that, let's say we have two qubits, and if we measure the first qubit, if we found it 0, so that second qubit should be 0 as well. So their results should be, it's correlated. And similarly, if we find the first one to be 1, the other one will be 1 as well. So we cannot find one of them 1, the other one is 0. So they have to share the same value, even though if they are several light years away, like one here on Earth and the other one on another planet, they will have to have the same value. So I'll jump to the quantum supremacy, which is I'll highlight two. So I want to briefly touch on two key principles, the one that I introduced before, which is the quantum superposition and entanglement, and their advantage in achieving quantum supremacy. So quantum superposition allows qubits to exist in multiple states, as we said before, not only 0 or 1, but multiple states, 0 and 1 at the same time, which enables parallel processing and a significant boost in computational power. So also the increased performance accelerates problem solving across various applications. On the other hand, we have the quantum entanglement, which refers to the strong correlation between qubits, which can be thought as a kind of a communication between these. There is no actual communication, but they correlate with each other. So this unique property enhances both computational and efficiency. So in summary, these two principles from the foundation of quantum mechanics paved the way for groundbreaking advancements in the technology of problem solving and new ideas. So how does it look like to have a quantum computer? It means, so in the classic world, to store a single, if you have a single bit, 1 bit, what you can store on it is either 0 or 1. While if you have a single qubit, you can store 0 or 1, or both at the same time, 0 and 1 at the same time. So if you have a quantum machine that has 8 qubits, it's equivalent to if you have a 256-bit classical machine. Why? Because in this, you can, to store this amount of information, 256, you need a 256-bit in the classic machine. However, for in the quantum, you need only 8 qubits and can store the same amount of information, and you can do the processing in parallel as well. So let me here introduce one of the experiments that have been achieved in 2019 by Google. So they achieved the quantum supremacy that proved that quantum machines are far better than the classical machines. And what they did in this experiment is they tried to solve a problem which is random circuit sampling. And in this problem, they have a quantum machine that has only 52 qubits. And if I can zoom here just to show you, like using a classical machine, we need at least 10 years to solve this problem. However, with this quantum machine that has only 50 qubits, it solves this problem in seconds, which means this type of computation is really promising, and it might help us in the future. So what can we take advantage or benefits from this technology? So we can say we are here. The technology, it's at the beginning, and still there's some time until we have the quantum computing mature enough that will be far better than the classical computing that we have currently. Once you have a bigger machine that can solve so many problems, we can use them to solve so many problems that we struggled in the past. We can have a stronger machine learning models that they are already start building some of these, which called quantum machine learning. And also we can solve some of the simulations problems of finding new drugs or finding new solutions for problems that you couldn't solve in the past. And also for optimization, we have so many problems that you couldn't optimize their solutions using the classical computation, but with the quantum machines, we can do this. So despite the benefits that quantum machines brought to us, it brings also a threat. So this threat targets our encryption systems. So just to look here as an example to show you the threat here, we have RSA algorithm, which is one of the most widely used encryption algorithm in the world. It is a standard, and every system is rely on this algorithm or similar to the same problem, which is factorization. So to break this algorithm using classical machine, it's represented here in the blue line here. And the x-axis represents the key length, and the y-axis represents the time, how much time you need to break this algorithm. So let's assume the key length of RSA is 512. It shows here like you need like a classical machine might break this key in 1 hour. So in 1 hour, this key is broken. What about if we have it 1024 bit length? So a classical machine might require like 8,000 years until this key will be broken. So the larger the key, the harder the problem becomes. And as you can see, if it is 2048, you need number of years, maybe the age of the universe, until a classical machine can break this algorithm. So by increasing the key, the complexity of solving this problem increases exponentially. However, if we have a quantum machine, the complexity of solving this problem or breaking this encryption, it's linear. How? Just by increasing the key a little bit. In the classic world, by increasing it a little bit, you are adding millions years ahead. But here, by increasing the key, adding few qubits will tackle the problem and will keep the machine ahead to crack the system. So by this is the threat that we are currently dealing with, and we should provide solutions for it. So this is the main algorithm that brought this threat to us, which is called Shor algorithm. It's developed by Peter Shor, and this shows the complexity of solving it using Shor algorithm or classically, and see the gap between these, how it's solved faster. I will not dig deep into these algorithms because they need several sessions. Another algorithm, which is called Grover's algorithm. So in this algorithm, it helps us in search problem. It solves search problems. So just to show you what does it mean is, let's assume we have a data set here that has n record, and you are searching for an entry here. Let's say we have a list of names, and you are searching for somebody. Let's say you are searching for Grover, but you don't know where this Grover, because the list is not ordered. So what can you do? You will check this list one by one. Either you are writing program or manually or whatever. You will check one by one. So let's assume that Grover is here. So it means you have to check them all, which means the complexity of this algorithm is n. You have to check every single record. So this is the complexity of the search problem n. And Grover algorithm minimize the cost into the square root of n. So as you can see, the gap between this, we don't need to check n record, we just only need to check a square root of n. So yeah, just to jump to a really important concept before going deep into the security. If we have a binary system or binary numbers to represent them, so if you have one bit, you will have two outcomes, either 0 or 1. If you have 2 bits, it means you have 4, either 0, 0, 0, 1, 1, 0, 1, 1. So what we are looking for here is the number of possible combinations. 3 bits, it means 8 combinations. 0, 0, 0, 0, 1, 1, 1, 0, which means the number of them 8. If we have 4 bits, the number is 16. So here is this table shows the number of possible combinations. It depends on the number of bits that we have. If we have 4, we have 16. If we have 8, we have 256. If we have like 64, we have 4.2 times 10 to the power n number of combinations. So why we need this? Because it defines the security of the systems in a minute. So the key length is the security bits, which is the number of bits in the key represent the key size. So how long the key is this, it's called the security bit, and it determines encryption strength, if it's strong or not. And back to the key size is this: more bits means stronger encryption. NIST announced these security levels, and we have 5 security levels, and they took 2 main algorithms as the benchmark here, like EES and SHA algorithm. So we have level 1, level 2, level 3, level 4, level 5. So based on the strength and the number of bits as well. So if I can jump here to show you, we have here the symmetric algorithms, which is, let's say, EES, the number of bits. But for the asymmetric algorithms, these ones that are broken now, the number of bits difference. Like here for the RSA, the number of bits is 480, but this 480, it's only equivalent to 48 of symmetric. Like 1,242, 248 is equivalent to 8-bit of symmetric. So this is why ES is the benchmark that we compare all the algorithms to it, how the security length. So this is just to compare these two algorithms. And why we are talking about the security bits, it's mainly to as a countermeasure against brute force attack. So if you cannot break the algorithm, what can you do? You will try all the possible combinations. And this is where, if all possible combinations are really huge, you cannot solve this. So let's assume the security bit that the system provides is 128-bit, and 128-bit means, maybe I have it here. So the number of possible combination is 3.4 times 10 to the power 38, which means, like here in terms of in words, it means billions of years required for powerful computer to crack the algorithm. Just if you have 128, it means billions of years you need to break the system, which means the system is really secure if it's 128 or more. So to recap our classical algorithms in terms of the quantum threat, here this is the security bits that we talked before, 128, which is from here beyond we can call it secure. And here we have the symmetric algorithms, RSA, elliptic curve, Diffie-Hellman, Al-Jamal, or others. All these algorithms are broken once a quantum machine is there. So we can't say they are secure. They are not secure anymore in the quantum era. We mean here in the quantum, after a quantum machine is there. However, we have these algorithms, EES, it provides us now, currently, it provides us with 128-bit. But once a quantum machine is there, with the Grover algorithm, the bit strength of this algorithm will drop half to 64, which means it's not secure anymore. Also 192, yes, classically it's secure, but with a quantum machine, it's not secure anymore. However, 256, it drops to 128, and 128 is still secure. That's why I depicted here in green, which means secure, and this color for it's not secure. Similarly, for the hash functions, like for this one, it drops into 85-bit, which means it's not secure anymore. So when we see quantum machines can break these algorithms, are these algorithms vulnerable to being broken by any quantum machine? And the answer is no, not any computer. So we have different types of quantum computers. Some of them are so specific, they only solve a single problem, not general problems. And there is no specific machine that cracks system. These are just general, like specific for some problems. So what we are looking for and what everybody is looking for is universal quantum machine. Why? Because it solves several types of problems. And one of the most important problems that it can solve is the cryptography. So only a universal quantum machine can break our systems. So many companies are working on this, trying to come up with a machine like that can help, that will brought us the quantum advantage and also the threat, maybe. So let's assume we have a universal quantum machine, and not any universal quantum machine can break our systems. Why? Because there are two main factors that a machine should balance or overcome, two main challenges. We need to increase the number of qubits. Let's zoom here. So what we need to increase the number of qubits, as we discussed before, the more qubits, the more space we can, or the more possibilities we can handle. So, but increasing the number of qubits is not enough. We need to minimize the error rate. One of the main problems for quantum machines is the error rate. So we need more qubits, but low error rate. Let's assume the error rate is this. So as you can see, it doesn't matter if you increase the number of qubits, as long as the error rate is high, it means there is no improvement if the error rate is high. The only improvement is when you have higher qubit with low error rate, which this is a really powerful quantum machine. So, so what are the solutions that we have? So our algorithms will be broken in the future. So what can we do? So there are two main solutions that you can do. Either we have quantum cryptography. We fight quantum with quantum solutions. What's good about these solutions? They are secure by nature. You cannot intercept a qubit and measure it without being detected. So they are really secure. However, there are several disadvantages of this technology, which is we need new infrastructure, we need new devices, and they do not support digital signatures, and they only work for short distances. We cannot have them for long distances. And we need time until we have them developed. So this solution is great, but it is not ready yet. So maybe in the future, it will be a good one, but what about the other solution, which is post-quantum cryptography? What does it mean? It means we are using normal algorithms that can run on our classical machines, algorithm that we can use it now, today, but it can resist quantum attacks. That's really good thing. And also they support all what we need. They support encryption, key exchange, digital signatures, everything. The only problem with these algorithms is they are not fully tested. We need time to test them. So they are the one that we are moving forward for it, and everybody in the world is moving for this solution because it's quick and we can start building it now. NIST organization started in 2016, searching for algorithms, for post-quantum algorithms. And these algorithms, in July 2022, they announced the winners. Kyber is the first winner for key encapsulation mechanisms. And for digital signatures winners, we have 3 algorithms. Also, they announced 4 algorithms to be alternatives for Kyber if something happened, or if one of these proven to be secure, they might be another standard as well. However, in just few weeks after this announcement, Cyc algorithm get broken classically, not even by a quantum machine. So we are left with 3, maybe 1 or 2 of them will survive to the next round. So we have algorithms that we are calling them post-quantum algorithms, which means they can resist a quantum machine. Is it really true? Is this really right? Let's investigate. So if we list these algorithms, we can say for sure these algorithms secure against Shor algorithm. So post-quantum means these algorithms cannot be broken by Shor's algorithm. But what about Grover algorithm? Grover algorithm can affect them. This algorithm can minimize the strength of these algorithms, and some of them might be broken as well. So these algorithms will be weakened. And what about new other algorithms? We don't know yet. There are so many algorithms being proposed every day, and maybe in the future another algorithm that might break everything. Nobody knows. But for now, we will focus on Grover algorithm effects. So here we have Kuiper, McCluskey, and these algorithms, and they are both quantum, but we need to investigate their security bits. Are they really secure in the future? So Kuiper has 3 versions. And as we can see here, classically, they provide us with 128, 192, 256. But after a quantum machine is there, this one will be broken, this one will be broken, these 2 will be broken, this one will be broken, and not to mention Psych, it's already broken. So only this one in green might be secure, and maybe a more powerful quantum machine might break one of these as well, this level. And maybe it will take time until these might be affected. But for now, it seems they are really great alternatives or choices. Similarly, for digital signatures, we have 3 main algorithms here. And digital signatures, we only have these 3, and they are already in the final stage for standardization. And for the lithium, we have three alternatives, and this one will be broken in the future using Grover algorithm and maybe other algorithms. Only the lithium 3 and the lithium 5, they can withstand a quantum attack. Strange here, which is Falcon. Falcon, they only have 2 versions of this algorithm. And the first one, it provides classically 256 and 512. And as you can see here, even though it provides us with 256, after a quantum attack, it will be broken. Its security levels drops to 106 something after a Grover algorithm. So only Falcon 1024 will survive. So this is really strange here. If I can go back to show you why this is really, it requires a lot of research and investigation to before we move forward to do anything. So because any algorithm that you see here that is 256, all of them survived. All of them survived. All of them survived. Here, like for this one, anyone that's 256 survived. Even most of the algorithms versions that's 192 will survive after the quantum attacks, but not for Falcon, this one, which means this might raise a question about other algorithms as well. And this is one of the most important problems that we are facing now. Is it, can we really choose algorithm? Is it, we can't now choose any algorithm because we are not sure which one is really good, which one will survive, which one will be a great choice for the future. So why all that? Because if we have if we managed to have a quantum machine that balance between the number of qubits and also the error rate, and that implements new algorithm, not only Grover, maybe new other algorithm, so these systems might be broken. So yeah. So I'll try to conclude here by providing conclusions and recommendations as well in this regard. So as a conclusion for this discussion on preparing for the quantum computing era, let's just briefly summarize the key points to understand the significance in the context of cybersecurity. Quantum computers on the horizon. So while the full potential of quantum computers is still a few years away, we don't know yet, maybe 5 to 10 years until we will have really and actually a well powerful and working quantum machine. This quantum machine might really pose a threat to our systems, but it's crucial for us to start preparing now for their arrival. Why? We need to prepare now because once they are here, there is no back. We can't solve the problem anymore until if they already arrive, because they will be in use and our information will be decrypted daily. Not only that, our history will be decrypted. Why? Because attackers now they are not waiting for quantum machine. They are already intercepting data, collecting data, storing it for the future. And once we have a quantum machine, they will take it from the storage and decrypt it, and they will know the history of, like, especially for organizations, for governments, for companies, and so on. So, and not only to be ready, but also we need to understand their capabilities and limitations. We might use these quantum machines to secure us, not only to break our systems. We can use them to help, like a quantum key distribution, for generating keys that are really, really secure and cannot be broken by quantum machines. So also we need to to explore the quantum capability. It's important to know that not all quantum computers will be able to break classical algorithms. As I mentioned before, you might hear in the news, or a new quantum machine being developed by company X or something. So what type of quantum machine, and how it's working, what's the principle that this machine is working on it, and how it solves the problem, and what type of problem, and can it actually solve a cryptography problem, which is factorization? If yes, that's really a threat. Other than that, it might bring us advantage, but not a threat yet. So yeah, as the quantum advance, it would be aware of its potential impact existing system. So also, once we hear about post-quantum security and the algorithms, achieving post-quantum status doesn't automatically guarantee security. As we mentioned before, having post-quantum algorithm doesn't mean you are really secure. Why? Because some of these algorithms that are already post-quantum, they will get broken by the quantum machine. Not all of them, but some versions of these algorithms will get broken, as we mentioned earlier. So we must continue to invest in research and development to build robust quantum-resistant solutions and to stay ahead of the potential vulnerabilities. So also, one of the most important things that we should do is migration. We should start migrating now. With the growth of quantum computing, it's essential to begin migrating to post-quantum algorithms sooner than later. If we can't migrate now, we should be prepared. We should start planning for the migration now. And by proactively transitioning our systems, we can minimize the risks associated with the quantum computing advancements that might affect our secure systems. So to conclude my talk here, in closing, we look forward to quantum computing era, and it's vital to understand the challenges it presents and proactively develop strategies to secure our systems against emerging threats. And by staying ahead of the curve, we can better protect our digital infrastructure and maintain a strong foundation for cybersecurity in the quantum age. These are the references, and thank you. Any questions?
Thank you very much, Mohammed. That was very insightful, a little scary, of course, as always, when you hear about this. But it's good to be aware and protect all of our systems in advance. Thank you for that.
You're welcome.
So let me just check and see if we have any questions online to be asked of you. And we have one question. Should one wait until NIST completes the standardization of post-quantum cryptography before starting quantum-safe cryptography preparation?
Yeah, so this is a really interesting question. So we cannot, so in terms of migration, we cannot migrate until we have a new standard. But the problem is here we have two things that we should focus on, which is preparation and migration. We should separate between these two steps. We have preparation and we have actual migration. And the actual problem that we are facing and that will take time to do so is preparation. It will take so long time to prepare, not only to prepare, but to understand what we have, what systems that we are having, what algorithms that we are using, let's say in our organization, what type of algorithms, what's the key lengths, What the systems that maybe we have systems that are hard-coded. We can't even migrate them. So this process takes time. It will take so much time, and we should not wait for NIST to do this process. We can do this process, which is identifying what we have assets, identifying the algorithms, identifying the systems, like deciding, okay, when we will start migrating. And once we have the actual standards for the algorithms, we start replacing them.
Very good, thank you. And we do have one more question. I mean, you could just take a minute. Is it feasible to start migrating by implementing with non-standard based cryptography?
This is really an interesting question, because yes, we started by 70 algorithm. Not we, I mean NIST started by 70 algorithm. And last July, we ended up with about 8 algorithms. They are really, really good algorithms and secure. But like in 2 weeks after the announcement, one of them got broken. So let's assume we decided to choose this algorithm to migrate using it. So, and it got broken, so our systems will be in a real problem. So we should not migrate until NIST told us which one is the standard. Why? Because migration, it is a community work. Like, you should use the same algorithm that I will use. So we all use the same algorithm, which means we need somebody in the middle to organize this, which is NIST, will give us the algorithm. Okay, now all of us, let's use this. So start development will just waste time and maybe money.
So we all should have NIST on our speed dial at the moment, right?
Yes.
Okay, all right. Thank you very much, Mohammed. We do appreciate that. That was very interesting and very insightful. So I would like to introduce our next speaker at the Canadian Institute of Cybersecurity, and that would be Dr. Somayeh Sadeghi. And Dr. Somayeh received her PhD from the University of Malaysia in 2015. She was a research assistant at the University of Malaya for 4 years, working on multimedia forensics. She's currently a postdoctoral research fellow at the CIC at the University of New Brunswick, and she has been involved in several projects, including DNS Firewall for the Canadian Internet Registry Authority, or CIRA for short, post-quantum cryptography, IoT security. Her research interests include information security, network security, cryptography, and image processing. So welcome, Somayeh, and the floor is yours.
Hello, everyone. Thank you, Pam, for introducing me. Let me share my screen. Okay. Today, I'm going to talk about from theory to practice, assessing the viability of post-quantum cryptography for various applications. Here is my the outline of my presentation. First, I will go through the introduction, and then the state of post-quantum cryptography, and then the challenge and limitations of post-quantum cryptography, the potential applications of post-quantum, and finally the post-quantum schemes evaluation and conclusion. Okay, my colleague Mohammed already explained about what is the quantum computers and quantum computing. I will just go in brief about this, that quantum computing has a potential to revolutionize many fields in many sectors, for example, for healthcare or financial sectors, if we want to go in deep for drug discovery or anything related to artificial intelligence. And with the increasing of processing power of quantum computers, of course, they can break many encryption codes that are currently using, and they are not breakable by classical computers. As quantum computing technology progresses, we have to think about two main things. The first thing is that classical cryptographic algorithms will become definitely vulnerable to any kind of attacks, and there should be interest for creation of new cryptographic algorithms that are resistant to these kind of attacks. So what's the difference between quantum computing versus classical one? I will go just in general one, as Mohammed already explained, for example, about the qubits which are using in quantum or the bits in classical one. Of course, even now, nowadays, the classical one, they can compute very complex computations, for example, like in laboratory works. But in terms of quantum, they can process massive amount of complex data in reasonable time and even with much faster speeds. Now, what is the requirements for the deployment of post-quantum cryptography? Of course, the biggest challenge facing the post-quantum cryptography is the need for transition. So the smooth transition from traditional one to the post-quantum cryptography is very important. And the requirement to deploy from to post-quantum from classical one is that integration, it should be the new algorithms, they have to be integrated into existing systems without disrupting their functionalities. And the cryptographic algorithms that are going to be used, they have to be resistant to quantum attacks. Quantum computing has influence in different aspects. For example, now I want to look at the quantum computing impact on data transmission. Okay, as I already said, the quantum computers, they can break most of, I can say, or all of them, all of the encryption codes nowadays, because the current algorithms that are using for encryption, such as RSA or ECC, they can be breakable easily by quantum computers. So we have to come up with a solution. Post-quantum cryptography offers a solution to this problem. They will provide cryptographic algorithms, of course, that are resistant to quantum attacks. And also these algorithms should be secure against attackers who can access to these quantum computers. Let's look at the impact of quantum computer on communication protocols. This in our modern life nowadays, we are using communication protocols a lot. For example, when you are trying to send an email or you are doing any online transactions, these communication protocols play very important role. And the security of these communication protocols is very important. With coming of quantum computers, the security will be compromised. So we need to upgrade the existing communication protocols to be able to use during quantum computers. The security should be, we have to be sure about the security of communication protocols. We have different kind of communication protocols, for example, SSL, SSH, or IPsec. As these protocols, they will provide extra security to prevent from any kind of attacks, for example, tampering of data during transmissions in online transactions. So it's very important. Now we need to enhance the current algorithms and protocols for communication protocols, key exchange mechanism, and also authentication protocols. The key exchange in quantum computing. Key exchange also play a very important role, and one of the challenge that, for example, in traditional key exchange protocols, which rely on mathematical problems. And definitely these mathematical problems can be easily solved by quantum computers. For example, nowadays they are using Diffie-Hellman key exchange algorithms, and it can be easily brokeable by powerful quantum computers. So we have to come out with a secure way to exchange keys between two parties, which is really crucial for secure communications. And then let's look at the impact of quantum computing on digital certificates. Digital certificates, as well as communication protocols, for example, they have play a very important role in our daily life. They can be used in many areas, for example, for digital signature, for secure communication or authentication. And these quantum computers, when they come in, they have, of course, the potential to break down the public cryptography that are currently using. Currently, we are using the RSA and ECC, for example, as a public cryptographic algorithms, and definitely they will be broken by quantum computers. And the security of these digital certificates relies on difficulty of deriving the private key from the public key. And quantum computers, by using Shor algorithms, they can break this. And to address this issue, researchers, they have to come out with the post-quantum cryptographic algorithms that are resistant to quantum attacks. I mean, to be replaced by RSA or ECC, which are using in digital certificates. We have talked about digital certificates. Now we are talking about digital signatures, which are very, very important. In traditional one that are currently using by classical computers, a sender try to send a private key to sign a message, and then it will be verified by anyone who can access to their public key. And the security of these schemes currently relies on the difficulty of factoring large numbers. So it will be so simple for quantum computers to wants to solve this kind of factoring large numbers. Definitely by using Shor algorithms, they can do it. And it means that traditional digital signatures, which we are currently using, they are no longer secure against any attacks which are coming from quantum computers. And of course, we have to think about how to replace the current algorithms as digital certificates. Here also RSA, ECDSA also using in traditional digital signatures. So what's the difference between traditional one that currently we are using and post-quantum digital signatures? In post-quantum, these schemes are completely different. They are using mathematical problems that are really hard even for quantum computers to solve them. Same as lattice-based or hash-based schemes. And if we want to talk about the post-quantum digital signatures like XMSS, Sphinx, or Dilithium, they can offer good security in terms for the digital certificates. And also for this kind of the certificates, NIST already came out with the finalist algorithms, which are quantum resistant. For example, for lattice-based cryptography, Falcon and Dilithium are the finalists, which are good to be used in digital signatures. And for the hash-based cryptography, Sphinx is the best. Okay, now we want to talk about the different use cases that are using quantum computing, how quantum computing can influence on different use cases. This quantum computing definitely have potential applications. For example, like in different sectors, like drug discovery in health care sectors, or for example, to optimize the investment in financial institutions, or even it can be used in climate modeling to better understand the weather pattern, and also it can be used in for simulation of very complex systems, for example, the behavior of black holes. So the industrial use cases for post-quantum cryptography, of course, there are a lot of challenges with this post-quantum cryptography, but despite the challenge, we have several potential use cases. For example, securing the communication channels for government agencies or for financial institutions, which are carrying this very sensitive information, or even in healthcare, the patient's information privacy is very important. Or we can talk about the secure communication in Internet of Things, military and government communications. Let's look at in more details in each use case. For example, in terms of IT security, Internet of Things devices, quantum computing, of course, poses a threat to IT security by breaking the encryption used to secure IT devices. Most of the currently, for example, RSA using for encryption in these IT devices. So by coming quantum computers, definitely they won't be usable. And the solution for IT security is the post-quantum cryptography, which can secure IT devices and networks by providing a secure key exchange and secure digital signatures. For key exchange, for example, they can securely exchange a secret key between two parties, or in secure channels. Or for digital signatures, they can verify the authenticity and integrity of data transmitted between two parties. So if we want to provide a secure key exchange and digital signatures, post-quantum cryptography should come out with to be used to provide confidentiality and integrity of data transmitted between IoT devices. And one of the examples that they can be used is Kyber, which is the finalist that NIST announced in July 22. So now in more details, how IoT security will be affected by quantum computers, and how post-quantum cryptography can solve or enhance the security of devices. For example, we can talk about secure data storage. We can talk about secure data storage, for example, for encryption of data to protect sensitive information for any IoT devices. It's very important to have post-quantum cryptographic algorithms for encryption, or for secure communication protocols, for example, to secure communication between IoT devices and other systems, for example, between IoT devices or servers or gateways, that to be sure that transmission is doing securely. And for example, secure bootstrapping, to establish secure bootstrapping mechanism for IoT devices, that to be sure only authorized devices can connect to the network. And another sample, we can talk about the secure firmware updates, to secure firmware updates for IoT devices, ensure that updates are not tampered with or modified during the transmission. Okay, how quantum computing affect on healthcare? In healthcare, we have different scenarios that every day we are facing, for example, for electronic health records or for medical imaging or for healthcare data, that they have to be protected. And by using post-quantum cryptography in healthcare, of course, the quantum computers, they can enable faster and accurate simulations and data analysis and optimizations. And also they can enhance the security of healthcare data and protect patients' privacy, which is very important. In more details, how quantum computing can help in healthcare, for example, drug discovery. All the post-quantum cryptography algorithms, they can help to accelerate the drug discovery process, or in precision medicine, to analyze large amounts of generic data and then even develop a personalized treatment for each individuals. Or in terms of medical imaging, it can be the post-quantum cryptographic algorithms can be used to process large amounts of medical imaging data, for example, like MRI scans. And of course, they can come out with more accurate diagnosis and treatments. And also cybersecurity, which will be focused on protection of patients' data. How it can be helped quantum computing in financial sector. Financial sector is, I can say, is the most important organizations that will be affected because maybe currently most of the financial services are relying on RBC, for example, for encryption, and definitely with coming of quantum computers, all the private data in financial sectors will be affected, and even it can affect on the secure communication. Except data protection, secure communication also will be affected when we are doing any kind of, for example, online banking, payment systems, or digital wallets, or any cryptocurrency transactions. Definitely, all the financial sectors, they have to transmit from classical one to the post-quantum based on their system requirements. Another sector which is very important for government and is government and military. The post-quantum cryptography definitely offer a new generation of secure encryption algorithms that can be resistant to quantum attacks. And these algorithms, they can be used to secure informations and military communications to protect their sensitive information or data. And this post-quantum, they can offer the military organization different technical benefits like integration with existing system or secure key exchange. Here are some samples of the ways how post-quantum cryptography can help to secure military and government communications. They have to replace the secure key exchange with post-quantum one, post-quantum cryptography algorithms, digital signatures, even for confidentiality and integrity. And some of the applications we can talk about: secure communication between soldiers and commanders, or secure communication networks, or secure email messaging, and security of IT devices that are currently using in government and military sections. Okay, we have talked about the problems that are that will come out with the coming of post-quantum cryptography. Now we are using classical one. What's the solution? Here is our recommendation if we want to do a transition from classical one to the post-quantum one. So the first one is definitely using post-quantum cryptography algorithms. As my colleague Mohammed also explained, NIST come out with the 5 finalists in July 2022 For example, they can, in terms of key exchange, they can use Kyber. NIST announced Kyber is great because it has small encryption keys that two parties can exchange easily, and also the speed of operation in Kyber is very good. In terms of digital signatures, Dilithium, Falcon, and Sphinx are doing great. NIST recommend Dilithium as the primary algorithm, Falcon for the applications that they need smaller signature compared to Dilithium, and Sphinx Plus, although it's larger and slower than other two, but is still valuable as a backup. The other factor that we have to focus is digital identity. To be quantum resistant in digital identity, it's important to use quantum resistant algorithm, which will be used for authentication and authorization. And also secure communication for using, we have to think about the secure communication by using key exchange and digital signatures that are using post-quantum cryptography. Okay, let's go in more detail. We have talked about the general use cases. Now I will talk about in more details about the applications that are using quantum computers that can be helped to perform complex calculations. For example, we can talk about one application, secure download. In secure download, we have to be ensured that the safe transfer of data between two parties. And quantum computing can help to enhance the security of this process by using quantum key distribution. The other application we can say is feature activation. In feature activation, it will allow us to unlock additional features for our softwares, for example, and how quantum computing helping, it can enhance the security by using quantum random number generators. And in terms of another application, secure access control, definitely we have to ensure only authorized individuals have access to particular resources, and the quantum computing can enhance the security by using quantum fingerprints. Okay, we have talked about the problems and we talked about the solution that is post-quantum cryptography algorithms. How we can choose these algorithms? We have, for example, 5 algorithms, and how we can know that which algorithms each is more suitable to specific use cases or specific applications. We have to evaluate all the algorithms with, based on different factors. For example, the primary consideration is security. Definitely security of the algorithms is very important. And the algorithms came out with 3 levels of security, level 1, level 3, level 5. Definitely we will focus on the security level 5 for each algorithms. And then it will come to compatibility. They have to be compatible with existing systems, existing protocols, and application. And another factor is performance. It should be able to handle large data sets and efficiency in distributed environments. Of course, cost. Cost also is very important when you want to upgrade your systems to be quantum resistant. It's very important. And the other one is complexity of implementation, potential security vulnerabilities. The maintenance cost must also be evaluated. But the most important 2 factors are runtime and the memory requirements. These 2 key parameters are very, very important in terms of analysis of the algorithm, post-quantum cryptography algorithms. I will go in more details for runtime and memory requirements, the assessment of post-quantum algorithms in relationship to their suitability for different applications, of course, depends on runtime and memory usage. How much runtime, for example, we said in some cases Kyber, we can use it, how much runtime Kyber needs to encrypt the message. And these parameters, of course, play an important role in determining the feasibility of the post-quantum algorithms. So runtime, the impact, if we want to talk about the runtime, the impact of computational time for key generation, signature generation, verification, encryption or decryption directly influence the requirements concerning time. And if we want to talk about the memory usage, storing keys has an impact on the size of non-violent memory, such as, for example, RAM, and the size of the private and public key signature or ciphertext also should be considered. Okay, let's do some analysis in terms of time and memory requirements. NIST already announced Dilithium, Sphinx, and Falcon for signature-based algorithms. Based on our implementation for key generation, signing, and verification, for example, for Dilithium, we have these values for Sphinx and for Falcon. Based on the values, they are based on seconds. And then we have, these are the value that we have for the algorithms, post-quantum cryptography algorithms. These are post-quantum cryptography algorithms, but CAN-based. And the HQC, Kyber, Psych, and McEliece, we have them. So how we can find, for example, which specific algorithm is more suitable for any specific kind of use cases or applications? We have to come out with the requirement of that application and the requirement of the algorithm itself. For example, here, I just come out with one example, the application access control. For access control, we have 4 options. For example, HQC, Kyber, Psych, and McEliece. Sorry. Based on our analysis with the time of calculation for the algorithms and the time for access control, for key generation, access control for signing, access control for verification time, then we can decide whether which algorithms is best. For example, here we can say that HQC and Kyber is the best algorithm for this specific application in terms of time. Okay, if we want to talk about the memory analysis, still we have signature-based Dilithium, Sphinx, Falcon, the public key length. Of course, we have all this information for each algorithm. For example, for Dilithium, the length of the public key, the length of the secret key, and the length of the signature and verification. I just write down, for example, Dilithium, it can have the the length of the secret key will be low, or Sphinx and Falcon, based on data that we have already here. And then for the CAN-based algorithms, the length of key encryption and length of key decryptions, we can do some analysis. For example, we have the same application here based on same with the time here. But if we want to talk about in terms of memory analysis, we can say all the algorithms are suitable for this kind of application. But in terms of time, only HQC and Kyber are best for these specific applications. Okay, let's go to the conclusion. We have talked that quantum computers, definitely they can break many classical cryptographic algorithms. And then what is the solution? The solution is coming up with the post-quantum cryptography algorithms that are resistant to any attack that coming from quantum computers. And we have to do analysis to decide when we want to replace the classical one with the post-quantum one in different scenarios. If any specific organizations, they can have their own requirements. For example, for some organizations, time is the most important part of the factors that they have to consider, but for some of them, time is not so important. So these are the factors that we have to think about: the security, the compatibility, standardization, performance, scalability, and efficiency of the algorithms, and of course the cost, complexity, runtime, and memory. That these last two factors are most important. And by carefully evaluating these factors, organizations, they can determine the suitable post-quantum algorithms for the specific use cases that they can be used. That's all about my talk. If you have any questions, I would be happy.
Thank you very much, Somayeh. Very insightful. And just like Mohammed, we all need to be on our toes and be preparing for this as it comes down towards us over the next few years.
Yeah, definitely.
So we do have one question for you, Somayeh, if you will. How can post-quantum computing provide confidentiality and integrity of data transmitted between IoT devices?
Okay, that's a good question, because the security of IoT devices nowadays is very, very important, as they are coming out in different sectors. For example, in healthcare or in financial sectors. The security of these devices are very important, and post-quantum cryptography, it can provide confidentiality and integrity of data transmitted between IoT devices, for example, by using the algorithms that are designed to be resistant to attacks by quantum computers. For example, in traditional cryptography, most widely algorithms using like RSA or Diffenhellman, they will be breakable, which are currently using in IoT devices for encryption. By using post-quantum cryptography algorithms for encryption and authentication, IoT devices, definitely they can transmit data securely without worrying about the potential, for example, for quantum attacks in the future. And also, post-quantum cryptography, it can help to ensure the confidentiality and integrity of sensitive information in IoT devices, such as, for example, personal and financial data, or critical infrastructure systems that rely on IoT devices.
Great, thank you very much for that. We do have one more question for you, Somayeh.
Okay.
What role do end users and consumers play in the adoption of post-quantum and hybrid cryptography?
Can you repeat it again? Sorry.
I certainly can. What role do end users and consumers play in the adoption of post-quantum and hybrid cryptography?
Okay, if we want to talk about the role of end users, definitely it's very important, same as our current lives by using classical computers. The role of end users is very, very important. And if I want to talk about the hybrid transitions, I mean, they have to think about the replacing of the classical cryptographies with the post-quantum cryptography.
Excellent. Thank you very much.
Appreciate.
Appreciate your time, Somayeh, and we shall move on to our third presenter from CIC, Dr. Vikas Chouhan. And Dr. Vikas is currently a postdoctoral fellow at the Canadian Institute for Cybersecurity at the University of New Brunswick in Fredericton. He received both his Masters of Technology and PhD degrees in Computer Science and Engineering from the Indian Institute of Technology, Rourke, India. He has several publications in reputed journals and conferences. He has served as the program committee member and reviewer of several international conferences. His research interests include cloud computing, cloud security and privacy, information security and reliability, blockchain technology, and of course, post-quantum security, which is the topic that he'll discuss now. Welcome, Vikas, over to you.
Yeah, thank you, Pam, for introducing me. Yeah, I will continue my presentation. So first, let me share my screen. Okay, then. So good afternoon to all of you. Today is my talk on beyond classical versus post-quantum, a hybrid approach for the quantum era. So these are the outline of my presentations, where I first discuss quantum computing and their threats, and then I discuss classical versus post-quantum, their strengths and challenges. Then I will deep dive into the hybrid approaches for key encapsulation, signature, and for public key infrastructure and their implementations. Then I will finally provide some recommendations and summarize the presentation. So here, the quantum computing is already explained by my colleague, but some audience is joined directly my presentation. Therefore, I give some overview related to the quantum. So now here, quantum era refers to the hypothetical period of time in which quantum technologies such as the quantum computing, quantum machines, quantum communications, quantum sensing become a widespread and revolutionize the many aspects of our lives. So here, quantum cryptography is based on the quantum mechanical phenomena, which can solve the complex mathematical problem quickly, which can pose the threat to the modern public key encryptions. So here, several threats associated with the arrival of quantum machines. Here we can see that the cryptography is the one of the biggest threat of quantum computing, because many encryption algorithms that are currently used, like RSA, ECC, could be broken easily with the sufficient large quantum machines. So here, because the quantum computers has the huge capability to solve the complex mathematical problem, nowadays what happened, there is a harvest style threat exists. That means they currently capture our ciphertext, and it will be a decrypt later when someone has the access of the quantum machine. And another threats are data breaches. That means someone has potential to break the security systems and steal sensitive information using quantum machine. And artificial intelligence, of course, because someone can use to create the quantum machines to generate the super intelligent AI system that could pose the threat to the or risk to the human life, humanity, and other things. And another aspect is the financial instability. That means it break into the financial institutions, maybe manipulate the transactions and manipulate the market also. And another is energy consumptions, because it required the significant amount of energy to operate. So there are several vulnerabilities, impact, and risk associated with the quantum computers, the arrival of quantum computers. So that is the compromise the sensitive informations. It could cause the financial losses. Here, digital signature be used for the authenticate the digital documents. So it can force the digital signature, which can lead the issue of identity theft. It undermines the security of high-level communication channels. It controls the blockchain network to perform some 51 plus attack to compromise the network with the more than 50% of the network peer, and can modify the transactions also. It can compromise the IoT network and gain the access to the sensitive information. So there are several pros and cons of arrival of quantum computing. So here, it can break the asymmetric cryptography, but the symmetric cryptography is not in danger. Speed is another pros, like exponentially faster computers, which is can solve the complex problems so easily than compared to the classical machines, and efficiency also because the multiple computations can be performed simultaneously. The cons is all the asymmetric cryptography is broken by using of the source algorithm. Another technological challenges associated with the quantum machines, like because it is sensitive to the environment, so there may be required a complex cooling systems and sometime error correcting mechanism to perform accurately. And high cost obvious for building and managing cost is associated with the quantum machines, and security risk also. So here we can see the when we expect the quantum machines and how it can break the currently used most famous algorithm is RSA 2048 in 24 hours. So there are some experts which contributed their thoughts about the likelihood of the arrival of quantum computers, and RSA will be broken in 2048 in 24 hours. So here you can see that there is an optimistic interpretation, like greater than 50% of likelihood in 15 years. So here you can see that let me use laser pointer. Yeah. So here asymmetric cryptography, which is secure in the classical environment, which are here 0-bit security in the quantum environments, which is broken by the source algorithm. Similarly, the symmetric cryptography is weakened from the classical security bit to the quantum security bit. It's almost half by using Grover's algorithm. So therefore, the NIST initiated some competitions to be for the post-quantum algorithm that are the secure against the quantum attack in the classical environment. So in the race, several candidates are participated, and at the end of the final third round, the algorithms are shown in the green color, like Crystal Kyber in the KM, and D-Lithium Falcon and Sphinx in the signature category are the winner of the third round, and they can be used as a secure post-quantum algorithm. And still some algorithm which is mentioned in the blue color are continuing participating in the fourth round. And Psych was the participant of the fourth round, but recently it broken, so only 3 algorithm is remain in the fourth round. So in the background, we can compare classical versus the post-quantum here. So classical security for post-public key cryptography, like if the cryptography which use the key pairs are currently broken with the quantum machines, and symmetric cryptography is already weakened. So the pros of and cons of the classical cryptographic algorithms are: the pros is proven security. That means widely used algorithm like RSA and ECC, their security are well tested and established over the time. And efficiency, that means it can be implemented quickly with the relatively low computational cost. And interoperability, that means we can use with the different platforms and different systems, ensuring interoperability and compatibility with the other systems. So the cons is it vulnerable to the attacks that is generated by the quantum computers, and limited key size is another cons, because in the classical cryptography, for example, we can consider the AES algorithm. So we have only three choices. We can use either 128-bit, 192-bit, or 256-bit keys. So so therefore there is some limitation associated with the classical cryptography, and some security vulnerability like a side channel is still there, and some chosen ciphertext attack can be performed on the classical cryptography. So for the post-quantum cryptography, we can say that the post-quantum cryptography is designed to be secure against both classical and post-quantum algorithms. So they can be registered against the quantum attack, because we need to require some protections. And it is the today's defense against the tomorrow's quantum hacker. And there are unknown impact on the code base also, like a longer key, longer message, and longer signature size is there for the post-quantum algorithm. Therefore, it has some running time issues, slower running time, and code agility issues also. So post-quantum cryptography need longer time to replace and specify it in the existing standard. For example, TLS, SSH, Internet Key Exchange, Public Key Cryptography, and SMI. So pros and cons of post-quantum cryptography is it provides the security against the attacks that is generated by the quantum machines. It provides the long-term security from classical and post-quantum attacks, and it is provide the compatibility with existing system, like a backward compatibility with the classical system. And cons is that it has this limited maturity, because the post-quantum algorithms are not yet to be matured as like classical cryptography, and it required higher computation cost because of larger key, larger message, and larger signature size. So here NIST suggests that the 128-bit symmetric security strength is provide the security until 2013 and beyond. And therefore, we recommend that we must consider the equivalence level of security for the classical cryptography and for the post-quantum cryptography. So basically, post-quantum cryptography are being developed as a goal of providing the long-term security against both classical and quantum attacks. So here, some symmetric encryption security is weakened by the Grover's algorithm, which consider only 128-bit quantum security, and which is equivalent to the 256-bit classical security. That is the another is the asymmetric cryptography, which is broken by the source algorithm. So we can replace that algorithm by considering the NIST suggested KEM and signature updated one, and we can consider only 128-bit quantum security for that. We need the performance and scalability is to be considered for the deployment of the post-quantum algorithms, and sometime education and awareness for the understand the potential risk and benefit of the post-quantum cryptography, and cost of development and deployment of post-quantum, which can provide the post-quantum solution that can be sometimes expensive and additional costs associated with the upgrading existing system and infrastructure. So therefore, we take all these things for the deployment of the post-quantum, and how hybrid approach address this problem. So we can say that it take the advantage of strength of the both classical and post-quantum algorithms, and it address these challenges of interoperability and integration with the existing system. Like classical cryptographic algorithm are widely used and well established. It can be easily integrated with the existing system and infrastructure. Post-quantum cryptography algorithm is designed to be secure against attack by the both classical and quantum computers. It provides the long-term security against the future advances in the computing technology. So therefore, we can also address the challenges of performance and scalability by dividing the work, like some task is done by the classical cryptography, and some tasks can be done by the post-quantum one in the hybrid scheme. So for the transitions to the quantum resistance cryptography, we require the careful planning and coordinations among the stakeholders like standardization bodies, industry organizations, government organizations. We should take care of the aspect of transition process, including security, algorithm performance, and secure implementations, compliance, and many more things. So we can also share the processing of computations, simulations, other results to take the input for the transitions process, and we can solve the limitations of the quantum computing in this way. So what is the hybrid? Hybrid means we need to be a combine multiple algorithms to make the robust solutions, which is provide the combined security and which is secure against both classical and post-quantum attacks. So here we can, at least two algorithms is required for the hybridizations. We can combine the multiple algorithms, like here you can see that we can combine the L algorithm here. So we likely play a role during transition for, we can combine like a classical and post-quantum algorithm. We can combine post-quantum with post-quantum to make a hybrid solution. So here reason is two reason is used for hybrid solution is better, because is hazing our bets. That means when the security of newer primitive is not yet certain. That means the post-quantum algorithm is currently used, is currently in testing phase, and we cannot say that these are the good one and which not able to be a break. So we need some time to establish, it will establish over the time. But the security of older primitives is already in question, like from because of the arrival of quantum machines. And to achieve the security and functionality both in the post-quantum aware and in backward compatible way with the not yet upgraded softwares. So the summary of hybridization is that it can reduce the risk during the transition and protect with the combined security of classical and post-quantum one. So these are the benefits, like security, because we can consider the security of classical plus post-quantum one. Efficiency, we can use the some tasks done by the classical and some tasks can be done by the post-quantum one. That, for example, we can generate the secrets from the classical cryptography and transmit via the post-quantum cryptography to secure transaction. And compatibility is provide the backward compatibility. It also allows the flexibility in designing. It can retain the backward compatibility and leverage the existing infrastructure. It enables the parallel uses of two independent cryptography schemes and compliance to the standard. It provides the smooth transitions, flexibility, and adaptability. It can achieve the security by combining the multiple algorithm for better security. At least one of the parallel algorithm used is secure, then our scheme is secure. It guarantees the security before the quantum. So it can be applied in wide range of applications, like we can use in KM, digital signature, key exchange, public key infrastructure. So these are the appropriate security property for hybrid scheme, like unforgeability. That means it ensures the signature can only be generated by the authorized signer and can't be forged by the attacker. And the non-separability property ensures that the attacker should not be able to drive the private key using some public key and signature. And it will provide the protected with the combined security of both classical and post-quantum. And it also supports the collision resistant property and non-repudiations, key security, resistance to the quantum attacks, interoperability, and performance. Means it should be a computationally efficient. So how can hybrid can be realized in the backward compatible way? So we can use some combiners to analyze the hybridization scheme. So for KEM combiner, we can combine the multiple KEM scheme to generate a resulting KEM which is secure against the classical and post-quantum attacks. So here a combiner is robust if resulting scheme is secure as long as one of the underlying primitive is secure. So there are many robust combiner exists like concatenations, XOR, KDF, and pseudo-random function. So how can we construct the hybrid signature? So we can choose 2 or more signature schemes with the different cryptographic properties, because if one is broken, so other scheme can provide the security. Hash of the message, we can use the secure hash function to provide the resistance to the collision attack. Sign the resulting hash using 1 or more chosen signatures, combine the security and resulting signature to form the hybrid signature, and verify the hybrid signature. In this way, we can construct the hybrid signature. And how can hybrid signature be realized in popular standard and software, ideally in the backward compatible way? So we can use some kind of X509 certificate, SSL, TLS, VPNs. They are support including of multiple signature in a certificate. So here, similarly for the signature, we can use the combine the multiple signature to generate the robust signature that is secure from classical and post-quantum attacks. So here we can say that the robust combiner, if the resulting scheme is secure as long as one of the underlying primitive is secure. So there are many robust combiner for hash function, signature, and KEM. So here for particular for signature, we can use concatenation, nesting, dual nesting. Nesting means the output of one signature can be put as an input to the another signature scheme to make a robust signature. So in here you can see that a document which is signed by the post-quantum signature and classical signature. So we can say that this document is signed twice. And at the receiver end, we need to verify both signature. So therefore we can achieve the security from the both signature via hybrid scheme. So here are some security notions for the types of adversaries. So here you can see that the capital X represent whether the adversary is classical and quantum. So quantum is represented by the capital Q. So here X represent the adversaries during the period in which it can interact with the signing oracle. So small y here in the notation represent whether the security adversary is classical, represented by the small c, and quantum represented by the small q. At that time, they will interact with the signing oracle, and Z is represent the adversary is after the period in which it can interact with the signing oracle. Capital C is represent as a classical, and capital Q represent the quantum one. So here you can see that C, this is the notation of adversaries type, which is the before the interact with the signing oracle, and last C is represent the after interaction with the signing oracle. So this is how attacker has the machine before and after the interaction with the signing oracle, and how they interact with the signing oracle. So in the last one, you can see that the attacker has the quantum signing oracle, and before and after they have the access of the quantum machine also. So here some notions like implications and separations. So here we can say that the B2A, that means every B secure scheme is also A secure, means every quantum secure scheme is classical secure scheme. And another notions is A separation B, that means there exists a secure scheme that are not B secure, means if there exists classical secure schemes, so there is no guarantee they are the quantum secure. So goal of non-separability is prevent an attacker from taking hybrid signature and turning it into the sum that verify accept as coming from a single signature. And the main goal is it used for the misrepresenting the signer's original intention, which is presented in the Nina's Bindal paper. So how can we analyze the hybrid in the public key infrastructure? So here we can utilize the X509 certificate, which has some TBS certificate, that is the to be signed certificate, which is not signed yet, contains some informations with extension field. And after signing, we have the complete certificate. So the challenge is this certificate can store exactly one subject public key and one signature is there. So these make the backward compatible hybrid certificate challenging. So for constructing hybrid signature, we need the two public key and two signatures. So what we can do, we can utilize the version 3 of X509 certificate that provide the extension field. So we have different approaches. Like here, dual certificate means we can use the two certificate, one for the classical one, one for the post-quantum one. Here you can see, and we can concatenate both using the combiner to make the dual certificate. And another approach is we can use the second certificate in the extension field. So here, standard X509 extension field we can use. So what we can do, we can first create the post-quantum certificate and put into the extension field of the classical certificate to perform kind of nesting. So, and this is a kind of example of dual message nested combiner. An alternate way is we can, without including the complete certificate in the extension field, we can use the specific public key and signature in the extension field to avoid redundancy. So here we have some libraries for implementation of the post-quantum cryptography, and we can test the combinations also. So this library is implemented in C, is a Libox library, Open Quantum Safe library, and the plugins are available, so we can use in Python also. So for example, we can test the hybrid scheme like ECC combined with the Kyber for the KM. And for the signature, we can combine the RSA classical and D-lithium post-quantum algorithm to generate the hybrid signature. We can test in this library. And we perform some combinations of classical and post-quantum script to make the analyze the cost of hybridization. So what we did here, we did hybrid KM, like we combine the hybrid RSA, classical RSA to the make LEC is a post-quantum algorithm to generate the hybrid, and resulting size is 2 MB, greater than 2 MB. Similarly, for RSA combined with the Kyber, we have 13 KB size, and for RSA combined with the HQC, it's 49 KB size. For signature, we combine the RSA with the D-lithium, Falcon, and Sphinx, and we notice that the Sphinx required larger storage space, and similarly here with the make LEC are required highest storage speed. Similarly, we perform and we analyze the output of storage scheme for the KM, and we same combination is used, RSA with make LEC, Kyber, and HQC, and the resulting scheme is like almost 2 MB, because we need the additional information for storage like a private key also. Therefore, size is little bit more than the certificate. Similarly, for signature, we combine the RSA with the D-lithium, Falcon, and Sphinx, and resulting size we analyzed here. So do the large public key and signature cause the problem here? So extreme size of combinations, because the post-quantum algorithm, there is no one fit size quantum safe algorithm is available. Every algorithm is in different size, different signature size, different public key size, different private key size. So therefore, we have some compatibility issues, because some system and protocol may have some limitations on the size of the key and signature. And also computation overhead and performance degradation is there, because more resources cause the performance issue on the device with the limited processing power. Similarly, for network bandwidth and storage requirements, so this can be an issue in situation where bandwidth and storage space are limited. For example, embedded system and mobile devices with the limited data plans, so which can affect the bandwidth and storage space. So our recommendation is that the organization should start to prepare migration plan, and therefore we can get rid of the sum of the old insecure cryptography and put you in the right place to be ready for the post-quantum cryptography migration. So in the summary, we can say that to achieve the high level of security against both classical and quantum attacks, we should deploy the hybrid schemes, and it provides the backward compatibility. But the issue is that hybrid algorithm may be more complex than purely classical and purely quantum resistance solutions. It increases the cost and difficulty of implementing and maintaining the migrated system. Additional processing and overhead expenses is there, like computational, network, storage, and management overheads. And it can decrease some performance because the huge size of the key and signatures, and it required modification effort in the current standards and solutions, but it provide more security, but with the little performance issues. But every organization should start to prepare the migrations to before arrival of quantum machines, so we can ensure that our system are secure and no one can perform any kind of attack or kind of harvest style threats. So this is all over my presentations. These are my references, and thank you. If you have any questions, please ask, and here is my contact details is there. If you have any question, you can ask, email to me.
Very interesting. Thank you, Vikas. So it's good to know that we have a hybrid opportunity. It isn't like pull the plug and tomorrow we have quantum. So there's a hybrid solution in regards to approaching that. That's good to hear. And we do have one question for you. About 2 minutes we've got left. If you could answer the question.
Yes.
Are hybrid solutions truly superior to post-quantum solutions?
Okay. So basically, if we talk about the hybrid solution, it depends on the specific use case and the goals of the system being designed. So for example, some specific requirement of the system, including security, performance, and compatibility. So in general, hybrid solution can provide some advantage over the post-quantum cryptography with some little overhead. So I already talked about that the post-quantum cryptography is not still tested and not yet mature as the classical cryptography, but the classical cryptographies also have some quantum threats. So therefore we need the hybrid solutions to achieve more security, but it will reduce some performance. So if you, it depends on your requirements. Okay.
Very good. Thank you very much. Now this could be a really quick question. We have about, well, actually, no, I think we are done looking at my clock. So thank you for that, Vikas. I do appreciate all the insights.
Okay, thank you. Thank you very much.
Okay, great. And with that, we conclude the conversation from our three of our researchers at CIC. We do have many other interests going on at CIC. Please follow us on our social media, as well as you can take a look at our website, which is unb.cic.ca. And feel free to ask any questions. We're always interested to hear from other fellow researchers. Thank you for your time.